Okay, so yeah, I actually do think this example is pretty good. Okay, so let's say that we have our function f of x is x squared minus 1 over x, and let's say we want to draw the graph of this. Well, there's a lot of pieces that we actually want to consider here, right? We want to consider the zeros, we want to consider asymptotes, right? Which also kind of relates to the domain of the function, right? Because if I have a value outside of my domain, that's probably going to be dividing by 0, which means I would have an asymptote. So domain goes kind of hand in hand with asymptotes in most of these questions, right? Um, then we also want to consider, um, right, increasing slash decreasing, and what goes along with that, because we're going to talk about this from the context of the derivative, then we're also going to look at the derivative for extrema, right? And that ends up being almost kind of the same conversation. And then we're going to talk about concavity and inflection points, because those relate to the second derivative and kind of end up asking the same questions there. So what does this actually end up looking like? Well, we want to find first the zeros of this function, right? So when this function is equal to 0, oh, sorry, I think a better way to phrase this is I really want to say intercepts, right? So we mean x and y intercepts, and y intercepts. Now the x-intercepts are the zeros, right? Now to talk about y-intercepts, that's going to end up going into our asymptote and domain problem for this really specific example, but at least start off talking about the x-intercepts, aka when is the function equal to 0? Well, if x squared minus 1 over x is equal to 0, well, when I have a fraction that's equal to 0, the only way that's equal to 0 is if the top part is equal to 0. Or looking at this, if I multiply both sides by x, well, then I get x squared minus 1 equals x times 0 is still 0. Or again, if a fraction is equal to 0, the only way is if that top part is equal to 0. So that means x squared minus 1 has to be equal to 0. Well, how can I solve that? Well, if I add 1 to both sides, I get x squared is equal to 1, which then has solutions x is plus or minus the square root of 1. Well, hey, the square root of 1 is still just 1. So I have two zeros, x is plus or minus 1. So f of x is equal to 0 at x equals negative 1 and positive 1. Well, now to talk about y-intercepts, I would say what do I get when I plug in 0? Or sorry, y-intercept, right? There's only one. So f of 0, well, hey, 0 squared minus 1 over 0 does not exist. So this leads directly into our conversation about domain. What is the domain of this function? X squared minus 1 over x. Is there anything I'm not allowed to plug in? Well, yeah, 0 is not in domain. So really my domain would look like negative infinity to 0, union 0 to positive infinity, if we wrote it that way. But really this means we have an asymptote, a vertical asymptote at 0 for x value, right? A vertical asymptote does mean, right, it's the x equals 0 piece. Well, we want to know where we go up or down, so we actually want to take the left and right side limits, left and right hand limits of this function. Well, if I plug in something really small but positive, and then I square that, right? something like 0.001 squared, I get something really small but positive, right? And then minus 1, I'm going to be negative, but really small. And then on the bottom, sorry, negative, right? Something really small minus 1 is going to be something like negative 0.99999 potentially, right? So really close to negative 1 over something really small but positive. So negative, so all of these numbers are going to be negative, but I'm dividing by something that's getting smaller and smaller and smaller, so it's going to turn into something larger and larger and larger, but is still negative. So my left-hand limit is going to go to negative infinity. Sorry, that was my right-hand limit. Now I want to look at my left-hand limit. So the left-hand limit of x squared minus 1 over x, well, this is going to be something really, really small, but negative, so negative 0.001 squared minus 1. Well, that's going to be still, right, 0.001 squared is the same as negative 0.001 squared, so something really small but positive squared, sorry, really small but negative squared gives me really small but positive. And then I subtract 1, and I still get something like really close to negative 1. However, I'm plugging in something really, really small but negative, so that would look like dividing by something like negative 0.001. Well, no, a negative over a negative is a positive, but I'm dividing by really, really small things, so they become huge. So this is positive infinity. So to the right of 0, I go to negative infinity, and to the left of 0, I go to positive infinity. And that's really important to look at. However, that's not the only asymptotes that we may possibly have, right? Because what if I consider the limit as x goes to infinity of x squared minus 1 over x? Well, hey, I only care about the leading terms, so that looks like x squared over x, which is the limit as x goes to infinity. X squared divided by x is just x, so that's just going to go to x. I'm sorry, to infinity. Well, now the same thing with negative infinity. Limit as x goes to negative infinity. This is also just going to be the limit as x goes to negative infinity of x, which now goes to negative infinity. So is there any horizontal asymptote? No. Because even though I go to positive or negative infinity, depending on what side I am, I know that that's not going to any actual number, right? There's no number L that I have. So there's no y equals whatever number to draw my asymptote with. So there's no horizontal asymptotes for this function. Now the next thing that we want to talk about is when our function is increasing or decreasing in any possible extreme values, which means to do that, we're going to look at the derivative. So if f is x squared minus 1 over x, then f prime, we need to do the quotient rule. Well, the derivative of the first piece is 2x times the bottom, this is x, minus the top times the derivative of the bottom, so x squared minus 1 times the derivative of the bottom, derivative of x is just 1, all over the bottom squared, so x squared. Um, okay, so there's going to be a jump cut here somehow, some way. I worked out this entire problem, having made an incredibly small mistake in taking this derivative and simplifying it out. And I think I just did like 30 minutes of work that is all just gone now. Because I don't want to be confusing by including the stuff that I did wrong and make you doubt, like, if you take this derivative, what happens, right? So I don't want to confuse you, so I'm deleting all that, but just know I'm in anguish right now. Okay, so we took this part of derivative, right? Now 2x times x is 2x squared minus x squared minus 1 times 1. So this is minus x squared. And then negative 1 times the negative sign here turns to plus 1 over x squared. So this turns into 2x squared minus an x squared leaves me with 1 x squared, and then a plus 1 over x squared. So this is my derivative, and I want to find critical values where my derivative equals to 0 or does not exist. Well, this derivative, right, the top part would have to be equal to 0. So it is x squared plus 1 equal to 0. Well, hey, that has no solutions, right? That's saying x squared is equal to negative 1, which does not happen unless you're talking about complex and imaginary numbers, but this has no real solutions, right? However, to for the equation to not exist, or for the function to not exist at a value, that means the denominator would be equal to 0. So x squared is 0. Well, hey, that gives me one solution, x is 0. So my critical value is only x equal to 0. So to know where I'm increasing or decreasing, I just have to know what I'm doing to the left and to the right of 0. I broke the real number line into two intervals, to the left of 0 and to the right of 0, and I want to figure out what the derivative it's doing on each of those intervals. Just what is the sign of the derivative on those intervals. Well, if I plug in a number to the left of 0, like negative 1, I get negative 1 squared plus 1 over negative 1 squared. Well, this is 1 plus 1 over 1. 2 over 1 is 2. So that's positive. Well, now if I plug in positive 1 here, positive 1 squared over positive 1 plus 1 over positive 1 squared. That's also 2 over 1. So that is also positive. So my function should be increasing pretty much everywhere, right? Well, now I want to talk about concavity, and I guess a little side note here. Do we have any local extreme values? Well, my function must be increasing and then flatten out, and then increase again, or something like that, right? Really, it's not going to flatten out because that derivative just doesn't even exist there. But is that going to be an extreme value? Well, no, because the derivative did not have a sign change at that value. Well, okay, now we want to talk about the second derivative. So we want to take the derivative of our derivative, right, of this function. So the derivative of the top is 2x times the denominator, x squared, minus the top as is, x squared plus 1, times the derivative of the denominator, which is 2x, all over 2x squared, or sorry, the denominator squared, so x squared squared, which is x to the fourth. So I can simplify this. 2x times x squared is 2x cubed, minus 2x distributed to both of these parts is 2x cubed, plus 2x, all over x to the fourth. Well, now, once I distribute all of this gives me negative 2x, right? Because 2x cubed minus 2x cubed cancels to 0. So I'm only left with 2x on top. So 2x over x to the fourth, well, hey, that's negative 2x over x cubed, right? That x cancels on top and bottom. So if I want to determine the concavity, then I want to find these critical points here, which would mean we're equal to 0, or does not exist. Well, negative 2 is never going to be equal to 0, so really I want to know when the denominator would be equal to 0, because that means I must not exist. So I want x cubed equal to 0. Well, hey, that means x is equal to 0. So when I draw the number line, I want to figure out what I am to the left and to the right of 0. So let me plug in negative 1. That gives me negative 2 over negative 1 cubed, which is negative 2 over negative 1, which is 2, positive, right? And now I do negative 2 over positive 1 cubed to get negative 2 over 1, which is negative 2, which is negative at positive 1. So I am concave up to the left of 0, but concave down to the right of 0. So now that I have all of these pieces, can I use them to graph my function? Well, I know that my function has x-intercepts, right, is equal to 0 at -1 and +1. So I'm going to draw my function in red to make it really clear, but I have to go through these two coordinates. Well, I also figured out that at 0 I have a vertical asymptote. Specifically to the right of 0, I have to go to -infinity, and then to the left of 0, I go to +infinity. That's what these two pieces showed us right here, right? My left-hand limit is +infinity, my right-hand limit is -infinity. Well, why did I automatically do it with that kind of concavity? Well, it turns out there's only one real way to have those asymptotes, and that is to have the specific concavity that I drew right there. Well, now, where is my function increasing or decreasing? Or do I have any horizontal asymptotes? No, I don't have any horizontal asymptotes. So where am I increasing or decreasing? I determined that my function is increasing everywhere that it exists, right? It doesn't exist at 0, but it is increasing everywhere else. So we need to be going upwards, right, on both sides. Well, what is my concavity? I figured out I'm concave down everywhere to the right of 0 and concave up everywhere to the left of 0. Now, what are my left and right asymptotes, right? To the right, I need to go to +infinity. To the left, I need to go to -infinity. Let me read that again. So to the right, I go to +infinity. To the left, I go to -infinity. Right? So I need to be, again, concave up, but decreasing, which means I can only have one shape, right? I have to be like this. Well, now to the right, I need to be concave down, but increasing, which means I only get one shape. It must be like this. Right? I'm concave down to the right of 0, but still increasing, and I'm concave up to the left of 0 and still increasing as I go to the right. So this turns out to be the graph of my function. There's actually something kind of interesting happening here, and that is the idea of a slant asymptote is very weird, and that is because I have, right, on either ends of my function, right, this simplifies to x and x here, and it turns out if I like draw the line y equals x, then my asymptotes are kind of like going to behave like approach that slanted line, which is weird, and I'm not asking that we like see that right now. But the point is that I used, right, my x and y intercepts, my vertical and horizontal asymptotes, or lack thereof, where I'm increasing and decreasing, and where I'm concave up or down, and where I have inflection points to draw the graph of my derivative. Uh, so yeah, that's what this whole section is about, is looking at all of the properties of the function, properties of the derivative, and properties of the second derivative to draw the resulting graph. Very good.